May have more people popping in, but I think we'll get started for everyone who's on the call already. First of all, thanks for joining for our first virtual Hacienda Talk of 2021. We are thrilled to have Sean Sally as our speaker today. I want to start off by just contextualizing a bit about what he's going to be speaking on more. And that's that soils are in many ways, they're an unsung hero of our world. They're out of sight and definitely out of mind for most people, but they're the foundation to all that we see that above ground and to literally to the very life of the planet. They breathe and then they actually contribute to our atmosphere. They store water in really, really important ways. They change, but they change very slowly, but they can also disappear. They're, they're irreplaceable once you start to lose them through processes of erosion or when we pave over areas. It's very, very hard to get them back. The Conservancy's management is really focused on the habitats of the preserve. And you've heard us talk ad nauseum about grasslands and wildlife and the health of our forests, but the management that we choose to do on those above ground habitats do affect the soils, and likewise the soils affect how our management can benefit or detract from these systems. So it's really important that we think about soils in our decision making. One of the big initiatives that we've had recently in 2019, we kicked off the Grasslands Initiative. And this is a 5-year project where we're investing $2 million into advancing our land management on the preserve. And a key element of this initiative is adaptive management. And you can only do adaptive management if you have data to understand what's actually going on the ground. When I talk about adaptive management, what I mean is that it's a structured and iterative process of observing, evaluating, learning, and then adapting or changing what you're doing in accordance with what you're seeing on the ground. And to do that, we've been collecting lots of data. Ever since we started as the Conservancy, we've been collecting data, but really intensively since we started our grazing program in 2013. So we have all of this data, some of which we've been able to tap into and explore a bit, but a lot of which is getting more and more complicated with the questions that we're asking and the different treatments that we're implementing, whether it's grazing for short periods or grazing in a dry year or mowing an area or not grazing an area for a year. And all of those different things make statistical analysis very challenging. So Rodrigo and myself and the rest of the team realized that we needed to bring in some better expertise on some of these processes and also on analyzing this data. So we partnered with the USDA Agricultural Research Service as a part of the Grassland Initiative. And we funded Sean for the last year in his last year as a postdoc as a part of this collaboration. He is now happily employed, so he no longer has to be part of the postdoc grind. Now he works for the USDA's Natural Resource Conservation Service, which if any of you were in farming or agriculture 20 some years ago, I believe it was called the Soil Conservation Service. So it's a service that works with landowners and helps them to put in good practices on their land. But it also has a research arm of sorts that Sean works for. And they develop what we're going to be talking about today, which are ecological site descriptions. And I won't get into too much of that. I'll let Sean tell you more about that. But Sean is a soil scientist. He now, as I mentioned, is working for NRCS in Las Cruces, New Mexico. He's a fellow alum from Colorado State University, where we both got our PhDs. We were not there exactly at the same time. I did pass through some of the soils classes, and as I was joking with my mom, who is on this call, I nearly failed one of the classes. So I'm happy to leave the soil science to Sean for this project. He has very adeptly tried to navigate the pandemic, juggling job search and small children. He has 2 small children and a wife who also has a job, and our ongoing research. So I'm thrilled with what we've achieved, and I hope that you enjoy his talk this evening.
Thank you, Christy, for that introduction. It was really exciting to be a part of this Grassland Initiative and come out and visit the preserve a couple times that I'll talk about here in a bit. But I will go ahead and start my presentation. I think I have access for this. Yeah, Christy, can you see my slide, or do you see my notes?
We've got the right view. Looks good.
Perfect. All right. Uh, as Christy said, I am now with NRCS. I was with ARS. Both are with USDA. And there's a lot of alphabet soup when you work for the government. The Department of Agriculture has a lot of different agencies. ARS is the research arm. They conduct research to develop solutions to agricultural problems. NRCS is kind of a sister agency. They provide farmers and ranchers with financial, technical assistance for conservation programs on the ground. They interpret the science for the landowner or a conservation group. I want to also mention the Jornada. It's a research lab within ARS. Historically, they conducted grazing research in the desert Southwest, but the scientists with the Jornada, of which Rodrigo is actually an alum, developed these concepts of ecological sites, how they relate to soil, how the underlying vegetation dynamics are understood. And of note, way back when they first developed this, going back 20 years ago, it really was more of an independent research project. But it's now a program that is scaled. It's used by all the federal agencies on public land. It's seeing more buy-in by cooperators, stakeholders, all the way from state to private conservation groups. So it's really exciting that a conservation group like the Santa Lucia Conservancy brought some of us in to really understand the vegetation dynamics and how it relates to the soil of the preserve. I do want to talk a little bit about myself since you're just seeing me through a tiny little camera. But here's some photos of me over the past quite a few years. When I first went to college, my passion was geography, the spatial sciences, specifically cartography. I always wanted to make maps, but I had a really great academic advisor in Kansas is where I did my undergrad. And he said, you can't just make maps, you have to apply them somehow. You have to specialize in a field. Cartography is just a tool. So that's how I first got into the geosciences, specifically geology. I define geology as the study of the Earth's physical structure, its history, understanding the processes which shape the Earth. And with that geology background, I came into soil science, really interested in how, we understand soil, how soil evolves over a period of time. So soil, within the broader soil science community, that field studies soil genesis, soil formation, evolutions of ecosystems, was sort of a path that I've pursued. As a soil scientist, I got to travel the US, worked in very interesting areas with soil and ecology in the desert Southwest. This photo in the bottom left is feet from the southern border. This was, I think, pre-wall. But it was really interesting working down there, comparing that to frozen soils in Alaska, tidal salt marshes in Alaska, and really lucky that I got to come out and look at the soils there in the coastal prairies of California. I put the bottom right photo in there. I think everyone has a COVID story. So I'm going to tell you guys my COVID story. Um, I've always wanted to pack raft the Gila River. And the Gila River is the southernmost natural snow-fed river in the continental United States. It's a wilderness zone. So, no cell phones, no access points. You put in at one point, and 4 or 5 days later, you take out at another point. And a lot of you probably heard the stories of people who went on the Grand Canyon for 3 weeks, and when they came out, the world was different. Well, that was kind of similar to how we went in. And this was the last day of that trip. You can tell I probably have the biggest smile out of all of these photos in that particular one. But when we came out, I had, 50, 100 different text messages. The world is coming to an end. It was very interesting not being a part of that process of us going into these lockdowns like we are now. But I just wanted to give you a little bit of background of who I am, different places that I've worked. As Dr. Christie mentioned, my involvement with the Conservancy was part of a cooperative partnership between the Conservancy and the USDA. We are still working with the Conservancy to build better understanding of the soils and ecology on the preserve with the greater goal of using that information and data to provide expertise and advice on the rangeland ecology. That includes analysis of the real treasure trove of grazing, landscape data, management history. We're mapping the geographic distribution of different soils on the preserve. That's the project that I'm going to talk about tonight. And then there's research and analysis of the different ecosystems on the preserve to understand how they respond to different types of management. All of this is really to evaluate ecosystem response to the Conservancy's targeted grazing program with the greater goal of generating data-driven conservation programs using the best available science. This particular photo was when we visited a year ago. It was almost exactly a year ago. This is on the far western edge of the preserve called the Animus. You can see in the background, right here in the middle, Carmel Bay and Point Pinos in the background of Monterey. But this was a really diverse group of scientists. A crew from North Dakota came down. And that's actually how I got involved, was through them. But volunteers, scientists from the Conservancy, and even other soil scientists from NRCS were a part of this effort. But really beautiful time of year. We only had a couple foggy days, but we came to sample, and it was really incredible with the crew we had, what we were able to accomplish during that 2.5 weeks. After I got back, I did discover that I got into some poison oak that took a couple weeks to get past, but we won't mention that. We'll just talk about the exciting part of sampling soils in the preserve. Here's a quick outline. The talk title is Soil Tells a Story. So I'm going to talk tonight about what a soil is, what a soil scientist like me does. I'm going to describe the preserve, the geology, the soils of the coastal plain, the Santa Lucia Mountains, and in general, these coastal prairie ecosystems. Talk about what an ecological site is, how they're created and used, and then get a little technical with the novel methods of how modern soil scientists map soils. This soil here is from the Goodrich neighborhood. Before I move on, note just how black this soil is. Really rich in organic matter, very productive. And when I say productive, I mean a very healthy soil with the right nutrients to support plant growth. This is a classic grassland soil, just like grassland rich organic matter soils we see in the mid-continent. And yet these soils evolve or form very differently, which I will get to shortly. But the first part of my talk is actually going to be me showing you soils across the preserve and telling a story, and hopefully you see it as nonfiction. So what is a soil? This is a very shallow soil, um, easy to dig. Has a bedrock contact at 30 centimeters. So all the loose material on the top, that is what supports plant life. That is what I consider soil. There is a official definition um, of soil by, this was created by the Professional Society of Soil Scientists, and that's the Soil Science Society of America. Um, and this definition was only recently changed to include other planets. I was actually at the meeting in Phoenix 4 years ago when it was proposed. I was in the conference hall right next to the conference hall where they were debating this definition. But there were only 5 people sitting through my talk, and next door it was standing room only. I was probably going on about hierarchical classification of soils. That's not important. But the main ideas with this definition are that it is loose material that supports plants. That is how I define soil. If we could zoom out to the landscape that soil you were just looking at, this is the landscape that soil formed in. It looks very productive. It has desirable grass species. It has similar management and conservation concerns as many of the areas of the preserve, as far as how it's managed for biodiversity or grass species. And this landscape also has seen some shrubs growing into the area, and absence of a conservation management strategy. You could see a regime shift from a grassland ecosystem to a shrubland ecosystem. This area is just off of Robinson Canyon Road, just as you leave the preserve to the north. You can, while the above ground vegetation does look productive and rich in desirable grass species, the below ground tells us that this is a very shallow soil. What does that mean? Well, soil is the medium for plant growth. A very deep soil allows for the roots of a plant to have access to more nutrients, but more importantly, more soil water. Think of this as if you are a grass or a shrub or a forb or even a tree. Shallow soils hold very little water. What that means to the overall ecosystem is it will have an almost immediate response to drought, and probably quite more dramatic compared to a deeper soil. A deeper soil would have a large reservoir of soil water. And if the vegetation is deeply rooted in that soil, our understanding is that those soils, the deep soils, would be more resilient to drought, more resilient to a high intensive grazing strategy. So you could use this to your advantage depending upon the conservation goals that you set out. Here on the left is a diagram of soil that you would find in a college textbook. It shows a lot of things that I'm not going to go into full detail about, but the main point is that soil can be complicated. One like this is an older soil. It has developed over a long period of time, think tens of thousands of years. And when they're this age with the right climate, the right geology, they organize into these layers or horizons. Often a young soil would start with just bedrock, and then they take that long period of time to develop into something like this. But the main point is that these horizons reflect the climate, the geology, how water moves through that medium, how plants take advantage of soil water and nutrients. And I put these bullets up just to reiterate some of the definitions I talked about earlier. But this last point is how someone like me studies and understands the soil. We know, actually it was a soil scientist at Berkeley who came up with this 80 years ago. We know that soil forms as a function of climate, biology, topography, geology, time, and now we know that humans also impact those conditions, those factors that drive soil development. And I'm going to give you some examples of climate, of geology, of how different soils across the preserve are a reflection of these main factors. Uh, this is debated some, but I think most soil scientists agree that climate, one of the most important of those soil forming factors is climate. Since many of you live in California, either full or part-time, this may not be new, but from a soil and vegetation perspective, the climate is actually really unique compared to other parts of the world. The graph on the right shows temperature and precip. Note that the precip, so the precip is this line with blue dots, and temperature are the yellow triangles, with the right axis being precipitation in millimeters and the left axis being average temperature. Looking at this, there's a couple things that I pick up. It doesn't get below freezing. But more importantly, when it's the warmest, there's the least amount of precipitation. So there's a term I'm going to talk about, evapotranspiration, which is water moving from the soil to the atmosphere, either through regular evaporation or through transpiration, which is movement of that soil water through plants, sort of your biological pump. What is unique is the timing of this precipitation versus the temperature. More soil water is available when there is often less biological activity. What that means is water isn't as used by plants, and it is allowed to flow through the soil and come out in springs or creeks. This is a lot different than Kansas, where I grew up, where we have a saying, April showers bring May flowers. And what that means is we have a pulse of rain in the spring that fills the soil reservoir, so that most of western Kansas's plant growth happens during the start of the summer, when the air temperature is getting warmer. I kind of think of it as during these summer months where you have these red slashes, you're in a net soil water deficit. What that means, and I'm going to tell a story later on about this, we couldn't really adapt the concepts, the ideas, how we understand soil once we moved out to California. A lot of soil survey got its start in Nebraska and Iowa. And when we came out to California and started mapping soils across the whole state, there really was very poorly understood. But this kind of dichotomy of when your average temperature is high versus when you have that available precipitation is what drives a lot of what we see in the soil. This soil on the left is one that we dug up about halfway between the golf clubhouse and the hacienda on the preserve. And since we visited in January, there is a healthy amount of soil water bordering saturated conditions there at the bottom. And there was a number of these that we read into that water would be seeping out of the soil side and ponding in the bottom. But I wanted to highlight this overall climate and how that water does impact the soil. The other thing I wanted to talk about as it relates to climate is what happens, what other phenomenon happens during those summer months. The answer here is fog. There are two maps here that I present. The left one is a satellite-derived image by one of the weather satellites. And the right one is more of a detail of the Santa Lucia Preserve. And I highlight this just as your summertime is kicking into high gear with less and less available moisture. Those soils are drying out due to that evapotranspiration when plants and soil lose moisture. But the fog cover actually slows down that biological pump. So we have this really nice gradient of here on the north and western end of the preserve, where at least during this time from 1999 to 2009, your June to September, you have an average of 13 hours per day of fog cover that is then impacting, that biological pump, how the vegetation accesses the soil moisture. And I'm going to talk a little bit about some of the computer models we ran to predict where soil comes from. But one of the top predictor of our soil concepts and our soil properties was precipitation. The second one was fog. So fog, very important with how soil drives these ecosystems there on the preserve. Now we've reached story time in the presentation. So I'm going to take you through a couple different landscapes, show you photos of the soil, talk a little bit about, what I see when I look at the soil. But this is a area in the Goodrich neighborhood. Dr. Christie walked me through these neighborhoods earlier, so I think I have them all correct. This is also on the north and west end of the preserve, or the more coastal side. And it's the same landscape I talked about earlier with that very rich, healthy, relatively deep soil with no slope. But oh man, it is just chocked full of organic matter. I said this is a really productive soil. This was the first soil a year ago that we dug into. I have some other photos of us actually digging into the ground, but essentially we dug until we hit 1.5 meters or this parent material, which prevented us from digging deeper. And we described it. We look at the properties, we look at the roots, we look at the color. Color is actually one of those things that tell us quite a bit about soil. And we sampled it. And all of that information goes into our predictive models that helps us understand the spatial distribution of the soils across the preserve. I want to put this in contrast to another area. So this is more inland, further away from the ocean, further away from that fog. This is near the Portuguese Spring Trail on Black Mountain. And it's very similar geology, very similar slope, so how terrain and topography impact soil, where the only difference is the amount of available moisture, both in precip and in fog. And this looks very different to that very rich organic matter soil that I'm just waxing poetically about. But it kind of builds this dichotomy of what the soil looks like, how we describe it, from one end of the preserve all the way to the other. And here they are side by side. Like I said, these are very similar geology, with the only difference being the climate. The left being more coastal and the right being more inland. Moving on past the climate side of soil formation, I do want to talk about the geology. And I'm not an expert in California geology, but you have these accreted terrains. They came in, they're faulting and folding. It's really complex, and this map also is a very simple generalization of the geology in the area. And here's a general outline of where the preserve falls on this map. But there are really 3 different geologies, parent material, across the preserve. The Monterey Formation, which sometimes is called the Carmel Stone. It's mostly marine sedimentary rocks, sometimes some limestone. It's not very old. It's tertiary, so if my geology is correct, around 30 to 50 million years. And that's contrasted to these really old quartz-like rocks, quartz monzonite, quartz diorite. The geologist will tell you that quartz monzonite, similar to granite, but it's more deficient in potassium. Diorite has more sodium. But in general, it looks like granite. It behaves like granite. The chemistry is a little different. And I highlight this because the two main parent material is this Monterey Formation and this quartz monzonite. So looking at those two of how they operate across the preserve, let's go back to that first photo where we're on the Animus, the western edge of the preserve. Here you have a young soil. It's formed in around this Carmel stone, this rock, and it's very rich in organic matter. There's not too many horizons. That's why I say it's young. It's very shallow because it has that fog and the precipitation. It has a lot of organic matter. Compare that to another young soil that forms in that quartz monzonite. And this is also further away from the ocean. This is near the parking area at the base of Pinyon Peak, if you've hiked that. And it's sort of a weathered granite. We kind of have some different horizons forming here where it's a little darker red versus this light yellow, not much organic matter, but young. And you wouldn't know it by looking across the landscape because it looks really beautiful grassland. Comparing those two together, the Carmel stone versus this granite soil, it's kind of interesting to, build in the climate with the parent material. And you have to think about it from a plant. How are you accessing that moisture? What nutrients are available? What's the overlying climate that, is causing you to thrive or to not thrive? What's your management strategy? Are you grazing it really heavily or are you grazing it lightly? It gets complicated really quick. And you guys have a lot of different soils. It sure surprised me, the diversity, the complexity of different soils across the preserve. Here is one near Vasquez Trail. It's sort of in this valley oak savanna. It was sort of around a bend. This was kind of interesting because when we dug into it, we saw this really beautiful, I'd call it a pendant, but where you have this organic material kind of seeping down into this unweathered parent material, this unweathered geology. And just kind of talking about this a little bit, the interpretation that I had with this particular soil was this was one of those valley oak roots that was rooted into that deeper material. And once the tree died or fell over, the cavity left in place by that root then became the soil. So it's not all perfect horizons. It can look very different as you dig into it. And it kind of adds to that complexity. You can't just take a volume of soil and calculate the amount of water because there's variability with depth. It goes from 30 centimeters all the way down to 60 centimeters, this little different cavity of organic matter. Another soil that we visited, this is near the Pinyon Peak Gate and Robinson Canyon Road. You could see my colleague sampling soil right over there. I show this site because one of the soil scientists that came out with us has actually worked quite a bit in the area, and I was really excited for her to come out. And when we dug into the soil, she's like, I've never seen anything like this before. It is just a bizarre soil. it classified, I think the soil scientist who'd mapped this area a long time ago recognized that this soil does exist, but it's just a weird cocktail of wet conditions in a different type of parent material on a flat surface. So there's a lot going on to unpack, but it was definitely the weirdest one that we saw. And it formed, I think, more in kind of a sandstone, which is a different sand phase of that Monterey geology that I was talking about earlier. This is the east peak or east slope of Pinyon Peak. And Pinyon Peak is really weird because it's a mix of the Monterey Formation and that granite-like rock. But this was pretty exciting because the way it weathered between this topsoil and the bottom part of the soil was it kind of created chunks of that sandstone material. It was just really pretty to look at. But I did not expect at this particular area to have a soil this deep. The soil that I showed earlier that was the granite material is actually right here. And down there you have the granite, and up here you have that sedimentary rock. So there's a lot going on, a very complicated geology. The climate, I think we figured out, but the geology was just well beyond something that I wanted to tackle. But the soil concepts, I think, are pretty rock solid. Mapping soil on the Santa Lucia Preserve, there's the mandate for the best science practices for conservation, which specifically challenged us to identify soils that respond differently to management or disturbance. I'm going to talk a little bit about the concept that Christy talked about, the ecological site concept, and its definition, because ultimately that's what we're trying to do. The soil scientists have their own taxonomy and classification system, and it's not the same as the ecological site. And that kind of added another layer just because of, as I mentioned earlier, the complexity of the soil, the geology, and the really steep terrain, which complicates it even further. These are all the sample points we visited. I think no, not all of them. There are some more up here. I grabbed the wrong map. Moving on. The ecological site concept, or ecological site description, is a distinctive kind of land with specific characteristics, making it different from other kinds of land. So we're already in trouble based upon the variability on the preserve. And it produces a distinctive kind and amount of vegetation that responds to management actions and or natural disturbances. The most important part is how a soil and ecosystem responds to those disturbances. And embedded within this concept actually is the vegetation dynamics. That is called a state and transition model. So ecological sites help prioritize management by understanding the land's potential and its dynamics. So here on the right, we have a very, very simplified state and transition model of in one ecosystem would be grasses, and another ecosystem would be a shrubland. Boxes are states, so those are stable in the long term, a stable ecosystem that's due to those different interactions, physical, biotic, disturbance regime. And then you have these arrows, which are the drivers and mechanisms of the changes between states. And they can include fire, grazing, some introduction of plant species, mowing, or lack of those drivers. The ecological theory behind it is that there's some sort of threshold keeping it in one state or keeping it in another. In this case, working the land, grazing it, is what kept a state into a grass state. Compare that to shrubs, where lack of a fire regime, lack of grazing, the shrubs would increase. And, absent of that disturbance, it would stay as a shrub state. Well, it's not that simple. Um, I didn't capitalize the E or the T, but I do capitalize the E and the T here because there's certain thresholds that are very difficult to go back from. And this is common in most places in California, um, where if you lose your entire perennial grass cover and you move to an annual grass cover, um, there is an ecological threshold that's very difficult to get past. It requires a very intensive seeding program to move it back to that annual grass state. Like I said, this is a very simplified state and transition model. Often they have like shrubs with annuals, undesirable perennials, invasive weeds. But this ultimately is what we were brought in to do, was to understand these thresholds, to understand how different ecosystems respond to fire, to management, so that the conservation program that's put together by the preserve is using the best ecological theory, site specific with the soil models we're putting together. And this has become a challenge. The idea behind these stable states was developed in areas that are very different than California. And often they're difficult to come up with, but we are making really good progress, and I'm excited to be working with the crew on that. In general, perennial grass state versus a mixed annual grass state. When the land is not worked, you have an increased biomass. Just by the standing crop creates shade. How does that thatch change the landscape dynamics? So difference between an annual and a perennial grass. Annuals have to regrow from seed every year. They die at the end of each year. They leave this standing crop if it's not mowed, if it's not grazed, versus a perennial grass where the life cycle exceeds 2 years. When you plant a grass, say in a yard outside your house, to get it established, you often have to water for longer periods of time to have that water percolate deep into the soil. And that creates a deep, dense rooting mass that also helps ward off insects, plants, disease, getting back to the soil concept of how a grass roots into the soil. These two behave very, very differently. And once you move into an annual grass state, reestablishing a perennial grass is a challenge. Here is an area, I think also near the Animus, where you have a stable grass state and a stable shrub state. But you also have this recent transition from a shrub to a grass state, to where I think this area was mechanically removed. I don't know the exact dynamics. Christy, was this part of the fire?
Yeah, that was part of the fuel break that was put in on the west edge of the property last year.
Thank you. We didn't have a chance to talk about this slide yet. But, absence of some sort of ongoing disturbance regime, fire, grazing, mowing every year, what would happen would be this, now area that's been removed of shrubs will eventually go back to shrubs, absence of, those disturbances, that grazing, that fire, and that mowing. That ultimately is the underlying theory of the ecological sites. It gets complicated once you talk about invasives. What is the exact conservation plan that the Conservancy is trying to do? It may be different on various landscapes. Grazing may not be the ultimate goal. It may be biodiversity or endangered species. These are all different things to be considered. We're not trying to create a whole grass prairie across the entire preserve. There are different competing interests when we approach these conservation plans. I wanted to show kind of a general state and transition model. This was our starting point when we really dove into the different ecological sites. And historically, if everything was a native grass state, if you're more coastal, those tend to change to coyote brush shrubland through that reduced fire, reduced grazing, and really the only thing back to tip it back into this native grass state once it is this stable shrubland would be a very hot fire. You know, the more shrubs, the hotter the fire would be, or mechanical removal, which is what we're seeing in a lot of areas in California. Contrast that to a more inland trend where if there's a viable seed bank or reduced fire, you actually see these coastal prairies turn more into oak savannas. And then the only way to tip back from that oak savanna is through a crown fire or combination of drought. We're still digging into some of the specifics. I'm going to talk about that a little bit later of what we're planning next on that front. But it really requires a diverse group of scientists who understand the ecology, understand the soil, fire return intervals, people who've worked the land for years of different range sites across California. Only with a broad coalition of people can we really dig in to make sure we don't miss some of these dynamics. And those are some of the things that we're working on now moving forward. So why can't we just use the soil maps that Soil Survey did? As Christy said, the agency that I now work for used to be called the Soil Conservation Service, and they published a soil manuscript for Monterey County in 1978. And so much has happened since then. This was right when we had our first published soil taxonomy, how we classify soil. You know, that's at the time, you know, it was a little pamphlet. Now it's this tome that, you know, you have to get a PhD to understand how you classify soils. But the other thing, the soil maps and concepts of that time, especially on the preserve, were really broad. And that was because of two reasons. One, Soil Survey at that time was more focused on tillage cropland agriculture. They weren't concerned really with rangeland agriculture. So, you know, it was the goals, the priorities of Soil Survey. It wasn't a priority. The other thing is, as I mentioned earlier, these soils on the preserve are really, really variable. It's just an incredible diversity that would be very difficult to map at that day and age. And I'm going to show you some examples of what that soil map looks like versus some of the products that we're creating. So this is an area around the hacienda that I think many of you are familiar with. This is actually one of the data layers that the preserve had flown for a high resolution aerial photography. And this also included near infrared to where they could, with those data layers, see the active vegetation or plants that are, you know, photosynthetically active, you know, actively green. What a soil map looks like overlaid on this area really are these kind of polygons. I think more in a pejorative sense, a lot of people who work in digital soil mapping now say, you know, that these guys took crayons around a map and drew a boundary. And, you know, that it's not giving them that much credit because there was a lot of effort that went into these concepts. Compare that to one of the products that we created, which these digital soil maps, you know, you do see that the lines follow, or at least these grids, these little squares, they generally do follow the soil lines that were created, you know, in the 70s. But when you have a targeted grazing program like the preserve has, to where you're moving the electric fence, as soon as, you realize that that land is spent, or, for whatever reason, knowing exactly what ecological site is can really help how you manage that land, given this point specific soil concept. We've talked about will actually impact how those fences are put up, or at least that's the what we've been talking about. The other thing that is included with this, which I'm not showing just because it doesn't look very attractive, would be this confidence, this sort of accuracy of the model that we created. And say we're looking at the green here versus the yellow, which would be a loamy versus a loamy bottomland. How confident are we, based upon our computer models that we develop, that point, that pixel or square on the ground actually is that ecological site concept? And we have really good confidence in some areas. Other areas that we have lower confidence, might actually inform some additional soil sampling that we need to do to improve those models. But the way that I went about doing this is sort of this cutting edge digital soil mapping approach, where you take soil observations and this geographic data, and that includes water, geology, soil, topography, but really cool LIDAR, which is a very high resolution elevation model, kind of inform these geographic data layers that were used. The real value of this partnership is the Conservancy over the last 10, 20 years had collected this great wealth of information. But we used a machine learning approach with those soils observations, that geographic data, to do soil properties. So that would be clay, sand, silt, carbon, other nutrients like nitrogen, phosphorus. We were able to do a prediction of all those different soil chemical, physical properties and those classes. When I say class, that's like the soil name or the ecological site name. We were able to predict and create this uncertainty associated with this computer model, this algorithm that we ran. And the way that it works is we're kind of in this validation phase where we're looking at the uncertainty. We're seeing if that makes sense with the experts who have worked the land to then improve, the various different soil models that were created. There's Eve doing our machine learning for us. I did want to talk a little bit about the sampling strategy. We came in a year ago and we collected almost 50 soil. We dug 50 soil pits over the course of the 2.5 weeks. And there's no way we could have done that without the scientists from the Conservancy, the partnership, the people that came in from the USDA ARS. We had the California Conservation Corps, which were some volunteers, some different interns that are coming in with, this broad group that the Conservancy came together with. And here's a photo of me probably mansplaining how to dig a hole to this really great Conservation Corps staff. But oh my gosh, it was a fun trip. Christy, we need to come out and sample some more soil. I did take a photo of all the soil that we collected. The diversity on the preserve was just unbelievable. At every soil pit that we dug, we're excavating, 2 or 3 feet square, going down a meter, meter and a half, looking at different horizons, detecting differences, with the tools at our disposal, pH meters, all sorts of different tools. And we collected, these are 2-gallon bags that were bagged up at each pit, brought here. You could see the heater and the fan trying to dry them out. These were all sent to a lab in Nebraska for chemical and physical analysis, a laboratory analysis. And, that information helped us classify the soil, understand nutrient availability, but also, more importantly, to really get at understanding the variability of the different landscapes. But this is definitely the biggest sampling project I've been a part of. And we didn't just sample anywhere. One of the cool things with the machine learning approach that we took to predict the distribution of soil properties was that we could run these computer models to find exact points that would tell us the most amount of information possible. So each point was optimized with all those input geographic data layers collected by the preserve. And when it was first ran, it said we needed about the 50 sampling sites. But the computer models just randomly put them across the preserve in very difficult places to reach. So we actually tried a new approach that only is recently showing up, at least in the soil academic literature, where we put together a cost layer. So what that means is there's a cost the further you walk away from the road. And we're not lazy. I was willing to walk to all those sites in the original model, but these points represent the same amount of information, but we were able to go in and collect the soil samples with much more efficiency. So we did that from a certain distance from the road. So it would be a lower cost the closer to the road, and a higher cost the further away from the road. But we also created a very high cost next to the home sites because we didn't want to be sampling right next to the various properties. This map is around the Mesa Upper Patero neighborhood. And, lucky enough, all 4 of these sampling sites were pretty close to the road. And it was, bringing this cost layer, all the data that the preserve has collected over the past decades, and a really great team of scientists that can come in and target this to create, to get all the soil and to create these models. I was excited to create this specific layer, and it seemed to work out. The other issue that is a bit more on the scientific side, we were very interested in how the concepts we develop on the preserve can scale to other areas in California, the whole region. We have, through the Conservancy, a wealth of information with very specific soils. But these soils don't exactly match like a central concept of counties, of soil sampled a county over, or north of San Francisco, that would be like similar forming factors of the soil, but just a little different climate. So one of the things that we have, or at least to reconcile that, we have these other quantitative tools to calculate how similar or dissimilar any given soil is to another. So this is a similarity dendrogram. Essentially, the further you go up the tree, the more or the less similar it is. And from an ecological site, you have these 2, which would key out to a clayey, and these other 2, which would key out to a fine loamy ecological site. But overall, they still fit within this kind of fine clay group. One of the cool things about these algorithms that are available to soil scientists now is we can create this distance to understand how we could scale these concepts. I mean, we're creating this product for the preserve, but we also want to use the information that we're creating as a program across California, and understanding how similar or dissimilar those soils and concepts are that we have created on the preserve is very important from an agency standpoint, and why I'm still involved at the level that I am. Soil scientists like to call soils names. This is a Santa Lucia soil. We usually name them based upon the geography that they occur in. And this is a very common soil in the Santa Lucia highlands. So the namesake soil of the preserve, it's a well-drained soil, rangeland, historically a range grassland of what we consider the coastal prairie. Historically, it supported the perennial grasses. It formed in the parent material, the Monterey Formation, that geology that's pretty common across the preserve. It's a steeper slope, 25 to 75%. It has a wide range of elevation that it occurs at, 500 feet above sea level, all the way up to 3,000 feet above sea level, and variation of precip. But this is a very common soil that occurs on that Monterey Formation. So looking at the geology and the parent material will get you a long way at classifying these soils and understanding their dynamics. So to round up, if I hit an hour yet? Oh, I just did. I'll try to be quick. The soils at the preserve, they were challenging to understand, to map, but necessary to support the main goal, which is to build this data-driven conservation program using the best available scientific tools, and hopefully me telling stories about different soil and give examples will help convey how unique this part of the world is. For researchers who have, us researchers who have partnered with the Conservancy, we are still building and working on these state and transition models by analyzing the historic data collected by the preserve. And I've said this many times to the scientists, that they have just incredible data sets to build these models of ecological potential, ecosystem dynamics across a very diverse assemblage of soil. And something like this requires a broader partnership of other agency scientists, land managers who've worked the land, a bigger coalition of scientists who understand fire regimes, conservation programs, digital soil mapping, and modern problems require modern solutions. And that's where we're working now, or building these ecosystem models of how they respond to disturbance. But hopefully you have some more knowledge of what a soil is, and more importantly, have a better understanding of the challenges that face the Conservancy. This is again that photo of, I'm here in green. These are my colleagues from North Dakota. They were really excited to wear short sleeves and shorts when they were coming down here in January. But I was just so excited to see this coastal grassland soil. This is in the Goodrich neighborhood. The history of soil survey began in the mid-continent in Iowa, Nebraska. And, this is a grassland soil, but it just looks so different. It behaves different. The climate is different. We actually had to stretch our taxonomy to call this a grassland soil, because they were built, our classification scheme was built in the mid-continent. But of all the places I've been, in the desert Southwest, Kansas, Colorado, where I did some of my grad work, Alaska, this is definitely one of those bucket list soils that I was pretty excited to sample in. But that's all I had. Hopefully you have a greater appreciation of soil. You have to dig a hole to understand what soil you're on. You have to have really top scientists like Christy and Rodrigo telling you what the history of that land is, so that you can understand how it responds to disturbance, grazing, fire. And I, for one, feel very fortunate that I was a part of this project. So thank you.
Thanks, Sean. Good job. Presenting on Zoom is never easy because you don't get much from your audience, but I saw plenty of people leaned in, listening and checking out your maps. So I realize that we are definitely a little over time, so if you need to depart, we won't take it personally. We are appreciative that you're able to stay with us this whole time. But Sean and myself are available for questions if you have any. I saw a couple pop up in the chat. Pull those up. Actually, Sean, can you see them? I'm back on my phone because my internet.
Yeah, the first question by Rob Kingsley: did you consider collecting the soils reports required prior to construction from homeowners, or would collecting them be a valuable input to your machine learning approach? So this would have been soil information that's collected prior to construction of some of the homes. I wasn't aware that this data set was available.
That had occurred to me. I think it's a great suggestion. I don't know what data is included in that, but they definitely have geology reports.
The main thing, and I'm not familiar with the reports, but often what's collected by a soil scientist who has the certification and credentials, they're looking at how the clay behaves in response to water. Do they shrink and swell as they hydrate or dry out? So often with home construction, that type of soil report informs how thick your foundation needs to be so it doesn't crack. If you have a septic tank, how big of a leach field do you need? That's a very different field of soil science than what I'm doing or presented for this. But I have a feeling that's what that soil data probably was. If it was collected systematically, absolutely, I think it would inform these digital models that we've created.
Rob, Rob, if you're volunteering your report, we might take a look at what potential it might hold.
Yeah, happy to send it along.
Awesome, thanks. I love this kind of like collaborative, bringing it all together, whatever data exists.
The next question I might have Christy tackle. Have the many new fire breaks on the preserve revealed anything new or different?
Interesting. Thankfully, this most recent contingency line that went in along our eastern boundary did not unearth anything new, but it did go over an area that really freaked out the archaeologists and the fire crew during the Sobranes. At the very top of our part of Vasquez, where you're headed up to the very, not quite at the top, but about where you get to, there's a little rocky outcrop between Black Mountain and Vasquez. The soil got really, really dark there, and they worried that they'd come across a Native American midden. And so the archaeologists came out and they didn't find any other evidence that it might have been a midden, but that's something that they are always looking for, is any kind of evidence of archaeology. I can't think of anything else that was particularly surprising, but it definitely showed us some cross sections of areas which, were interesting to look at, but not something I'd hoped would be revealed. Some of the lines got a little deep, as we've discussed before. So,
thank you, Christy. The next question, I think, is kind of in the same theme. Does the soil analysis hint at the fire history of the area? And I think with the fire return intervals, it happens at such, at least historically, such a narrow time frame, 5, 10, 20 years, where the soil, takes, a small millennia to form. One of the interesting aspects that the analysis, these digital soil models that were created, they used satellite data as an input layer. One of the geographic layers we had was, vegetation taken from, Landsat satellite going back. I only peeked at the last decade, but if we had historic aerial photography, going back to the 50s, and a lot of places in the world, you do have aerial photography that goes back, and I don't know if the preserve has looked into that, but you can look at areas that may have been grassland in the past and now is shrubland. The soil models, because it does use that input layer from the satellite imagery, it's saying it's in some cases a different soil underneath that shrub state than the grass state. But we haven't really dug into that data, just understanding the complexity. It wouldn't tell us the fire history, but it might tell us a potential of where you could take a shrubland and move it back to a grassland.
And that highlights one element of this project, which is that it was focused on the grasslands as a priority habitat that we're managing. We did not do any sampling in the woodlands or in the redwood forests or in the thick chaparral and coastal scrub. So we have very high confidence for the predictions in the grasslands of these soil models. But the future iteration of this project would be to continue this soil sampling and modeling across the different habitats, so we can get a really robust model for the entire property, not just the 5,200 acres that we're really focused on at the moment. So never-ending projects and opportunities. You'll get to come back out, Sean.
Looking forward to that. Another question, did we look at the watershed creek areas and above them to determine whether there is erosion happening that is problematic? That wasn't specifically part of the project that I'm doing, where we're classifying the soil. There are a lot of soil health tools at our disposal that once we understand the ecological sites, the soils of different landscapes, that could be part of an annual sampling strategy to see if an area is eroding or how healthy or resilient different landscapes are. And I have a number of colleagues with the lab that I work at down here that have developed those tools, but that's not something specifically that we've talked about yet. Christy, is there anything that you'd want to add to that?
No, there's some of that may show up in kind of tangentially in some of the stream monitoring data that's been going on for 19 years. And then we also have a master's project that is looking at some of the dry up stretches of the creeks and how those respond to wet and dry seasons. And that kind of data creates baselines that you could go back and you could look at the metrics from those projects and see how they've changed over time. It would give you a more high level view of what erosion processes are happening in the creek, but not something that we specifically were targeting with this project.
Sweeney Co. asked the question, we live in the Potrero Creek area and our soil has dirt similar to talcum powder. When it gets wet, it sticks to your shoes and gets thicker with each step. Someone told us this was volcanic ash. It possibly could be. Volcanic ash is one of those weird things that when it has to have the right conditions for it to be preserved. At least this is true in the mid-continent. I studied some volcanic soils in Wyoming, Colorado, and Kansas. And volcanic ash, in order for it to really be preserved, requires the deposition from the volcanic eruption, and then also often a soil or sediment capping it to where because volcanic ash is very erodible, in order for it to stay on the landscape, it has to have the right conditions. It is quite possible that it is volcanic ash. There is a soil that we classified in this area that did have a thin layer, and I could actually show you what it looks like. It is this soil, the second one from the right, and it has this kind of layer in it. And I don't know if this is similar to the one that you observe, but I interpret this as some sort of deposit and then a landslide that has capped it. And I mean, that's just me arm waving. I really don't know if that's true. It does match a soil that's mapped in the area. So at least this sort of habit, these soil properties by depth, very possibly could be a volcanic ashy soil.
Yeah, that color looks right.
Where kind of like the white band is.
Uh-huh.
Yeah, if I'm remembering correctly, I think that was up on the mesa. So it's a higher elevation, but not from your location.
Oh. It's weird stuff.
Sounds like it.
Okay, so when do the creek areas get looked at?
Oh, that from Karen as well. Well, we'll have to figure out another project. There's, as I often say about the preserve, there are far more opportunities and questions to answer than we have capacity or time. So yeah, we'll have to figure out what the question is and how we want to go about it.
Thank you, Karen. Jim asked, did your soil testing measure the health of microorganisms? Oh, that's from Ginger. No, soil health, and especially this type of understanding the microbial activity is exploding. A lot of scientists at different universities have whole programs built around understanding the soil microbiology. Only recently has NRCS on their research arm, so some of my colleagues, have they actively hiring a soil biologist to integrate some of these concepts that we're learning from soil microbiology into soil survey. And that hire, the interview starts next week for that position. So we're still behind the times from a soil survey agency understanding the microorganisms. And there's a lot of disagreement on the specific tests that you use to capture either that diversity or those functions. It's definitely outside of my field, but there is a lot of potential with interactions of soil survey with the work I presented and that field. It just hasn't really got going yet.
All right. Any other questions? Awesome. Well, thank you all for joining us this evening. Make sure that you keep track of the calendar. We've got some more events that we're lining up. I believe our next virtual Hacienda talk will be in April, and it'll be by Carrie Frangioso, who we've had speak before. She'll be updating us on some of her sudden oak death research and how the fires have been affecting their research. So for those of you that aren't familiar with their work, they had a landscape level project that they were already doing, which has now been affected by several different fires. And it's created a natural experiment of sorts where they're able to watch the response of our woodlands and our forests to these fires, and similarly look at how sudden oak death responds or is affected by the fire regime. So it's a pretty fascinating opportunity, and definitely science pivoting with opportunity on that one. So look for that in the calendar. And it was great to see so many faces. I hope you guys are doing well. Thank you, Sean. You did a great job.